All right, homework 21, we're going to start with explained and unexplained variation and the least squares regression line. First of all, they're going to do a bunch of the calculations for you, but you're going to have 3 different calculations that would normally be done, and you need to know what all of those things are. So the first one, when you have y hat minus the mean of y, is the sum of the squares regression line. They call it SSR, sum of squares, yep, regression. The next one, where you just have y minus y hat is SSE, sum of the squares error. Gives you the error. Sum of squares, you can almost read that S, error. So that one was the SSR. This one is the SSE. The last one, when you have y minus the mean of y with the bar over the top, you have SST, sum of squares total. So on this table here, the sum of the squares regression is 1.83, so forth. Sum of the squares error, 1.9140. Sum of the squares total, 3.7280. So, it says, bivariate data obtained for the paired values x and y are shown below in the table, labeled sample data. Here's my sample data. These data are plotted in a scatter plot in figure 1, so they plotted the points for you. They also put the equation of their regression line, which is y hat equals 1.95 plus 0.44x. So they've done all that work for you. It says in the calculations table, calculations involving observed values of y, the mean value of y, and then the values of y hat are predicted from the regression line. So for the data point 3.9, 4.5, the value of the residual is what? Round your answer to at least 2 decimal places. So what they're trying to tell you is really you're not even going to look at the 4.5. You're just going to look at this value here. That is the x value that you want. In your table for your sample data, you got 3.9 and 4.5. But if you put this into your equation for your line of best fit, what value do you get? So you're going to take the number for the x value of that data point, plug it into your equation. So y hat is going to equal 1.95 plus 0.44 times that x value, which is 3.9. And then you're just going to do that calculation. If you multiply all of that out and round your answer to at least 2 decimal places is what it tells you to do. If I grab a calculator here, I get 3.666 when I do that. So if I'm going to go ahead now on this one after I get that number, and now I have to find what the residual value is. So now what I'm going to do is I'm going to take the value that they said was going to be the x value and find what the difference is between those. So what I'm really doing is trying to find what the difference between the point where it would be on my line and the point that would be in my graph would be. So I'm going to say that in my original data point, I had 4.5. On my line of best fit, I had 3.666. I would subtract those two values, and the difference is what your residual value is. So I would get 0.834 when I subtract. Since I'm rounding to two decimal places, 0.83 would be my residual value between those 2 points. So we take the x value from the point, put it into our line of best fit equation to find out what the value on the line would be. And then we take the y value from the point, subtract the y value from the line to see what the difference between those 2 points is. Second part of this question says, the least squares regression line is given above is said to be the line which best fits the sample data. Best fits the sample data. The term best fits is used because the line has an equation that minimizes, and the line of best fit should minimize the error. So I'm going to use SSE here. The line of best fit minimizes your error. So the sum of squares error for these data. And so then what I'm going to do just is look in my table because they've already done my calculation. In this case, it's the 1.9140. 1.9140. So I just looked that number up in my table. That's the number for the sum of the squares error. I gotta move my thing because I can't see the bottom two questions here. Hopefully you have that written down. Bottom two parts of this, it says, I'm going to see if I can still keep that table there. The variation in the sample y values is explained by the estimated linear relationship between x and y given by, so when it asks for that, the variation is explained by, that one is going to be your SSR, the sum of the squares regression. The sum of the squares regression explains your variation. And then the same thing, I'm just going to look at my table, and since I moved it, it took off my labels, but this was my regression, this one was my error, this one was my total. So here's my regression. And then I'm just going to look at my table and pick out the number or put the number from that one, 1.8345. Whoops, I got to put it in the right spot, 1.8345. And the last one, it says the proportion of the total variation in the sample y can be explained by the estimated linear relationship between y and x. And in this case, what we're trying to find is what they call r squared. R squared is found by taking the sum of the squares regression number divided by the sum of the squares total number. So I'm again going to just look in my table. My sum of squares regression, 1.8345. My sum of the squares total, 3.7280. I'm going to divide those two numbers, round my answer to two decimal places. So again, if I just grab my calculator, 1.8345 divided by 3.7280 gives me 0.4920, so forth and so on. We're going to round our answer to two decimal places there. So if I round that off to two decimal places, 0.49 would be my answer. So again, just to make sure you have all your answers in here, 0.83 was our answer when we did that one. The sum of the squares error is my best fit, and the number for the sum of the squares error was 1.9140. So it's going to look something like that. All right, number two, pretty close to the same thing. If I move my thing. So in number two, it says bivariate data obtained for the paired values x and y are shown below in the table labeled sample data. So here's my sample data. The points are the points that are plotted over here in figure 1. It also shows you the regression line, the equation for the regression line, which is our line through here, y hat equals 3.06 plus 0.97x. The calculations in the table involve the observed y value, the mean of the y value, and the values of y hat, which are the values from your predicted regression line. So, be careful on here. They switch these around to make sure you're paying attention which is which. So when I have y minus y hat, that one is my sum of squares error. Y minus y hat. When I have y hat minus the mean of y hat minus the mean with the bar, that's the sum of the squares regression, SSR. And then when I have y minus the mean of y, that's my sum of squares total. So you want to watch for that because they switch them around and they don't always put them in the same order. So the variation sample y values that is not explained by the estimated linear relationship between x and y. When it asks you about the variance being not explained, then I am going to do the sum of squares error. Now if you read your chapter for chapter 11, it's going to explain all these things, so you might want to make sure you go back and look. But if it says variation not explained, it's a sum of the squares error. And then again, we're going to just look in our table. In our table here, we have 45.7727. The value of r squared is the proportion of the total variance in the sample y that is explained by the estimated linear relationship for x and y. For these data, what is the value of r squared? So that's the one we did last on the previous one. When we did r squared, we took the sum of the squares regression line and divided it by the sum of the squares total. And so my SSR number was 224.7529. My sum of the squares total number, 267.2120. 267.2120. Again, you're going to grab your calculator and divide out those two numbers. So, 224.7529 divided by 267.2120 gives me an answer of 0.8411, so forth and so on. But we know we only need to round it to 2 decimal places. So if we round that off to 2 decimal places, 0.84 is going to be what our r squared number is. Number 3, it says the least square regression line given above is said to be the line of best fit. Again, if you remember from problem 1, when it talks about the line of best fit, the term best fit is used because the line has an equation that minimizes the error again. So I'm going to have SSE, it minimizes my error. So variation is not explained by the error, and best fit is explained by the error, or is given for the error. So for my SSE number, same number we had before, 45.7727. 45.7727. And then the last one is the one where we did before. We had to find the value of the residual, kind of the distance between those 2 points from our actual dot and the point on our line. So we want to use the data point 590. 590, this data point right here. First thing we're going to do then is figure out if we use our equation and put in 590, what do we get for our y hat value? So y hat is going to be equal to 3.06 plus 0.97 times the x value, 59.0. We're going to find that value first. That's going to be the value of y on our line. Again, we're just going to grab our calculator. And figure that out. 3.06. So I get 60.29. 60.29 would be the y value right on the line at x being 59. So x being 59, here we are, if I could get pretty close anyway. 60.29 would be the y value of that point. Now we're trying to find the residual value between those 2 points, the point that was given and the point that's actually on the line. So on the point that was given, we were at 62.6. If I look right here or look in my table, so I'm going to take my 62.6 and subtract my 60.29. If I take 62.6 and I subtract my 60.29, I get 2.31. So my residual value is 2.31. All right, number 3, going to be the same thing. There we go. Wanted to get it as close to the top of the page as I could. Variant data obtained for the paired values x and y are shown in our table below again. Sample data. These data are plotted in the scatter plots. So each of the points that are made are the data in the table. And then we also have our least squares regression line. They give us that least squares regression line equation right here. The line is also on my table. In the calculations table, the calculations involving y, the mean of y, and the values of y hat, which are the values that we get right here on our line, predicted from the regression equation. So, we had a look. Here we have y minus the mean of y. So y minus the mean of y, if you remember, that's my SST value, sum of squares total. The middle one I take y hat minus the mean of y. Y hat minus the mean of y is my sum of squares regression. And then we have y minus y hat. Y minus y hat is my sum of squares error. So make sure you always look at your table because they switch those around, you get the right ones marked. Number 1, least square regression is given above is said to be the line which best fits the sample data. The term best fit is used because the line has an equation that minimizes, and if you remember from the previous 2, the line of best fit is going to minimize your error, so we're going to have the sum of squares error. Sum of square error number, we're just going to look in our table. 48.4865 is going to be my number there. This one is one we didn't have on number 1 or 2. It says the total variation. Notice the word total gives you a hint. The total variation in the sample is given by the sum of squares total. That makes sense, right? And again, we're just going to pick that number off the table. The number for the sum of squares total is the 297.7680. Next, we're going to do the proportion of the total variance in the sample values that can be explained by the estimator linear relationship of x and y. Again, that proportion is the same thing as when they ask for r squared. So 2 different ways they might ask it. Either they're going to ask for r squared, which is the proportion of the total variation. So proportion, I'm going to set up my fraction. We said we're going to take our SSR value divided by our SST value. The sum of squares regression divided by the sum of squares total. So in this case, we're going to take the 247.9325. We're going to divide it by the sum of square total, which is 297.7680. So we're just going to divide those 2 numbers. Go ahead, grab your calculator, punch that in. And so, I'll just grab my calculator and punch that in. 247.9325 divided by 297.7680. That gives me 0.832634, da 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 da. So, rounding that off to 2 decimal places, we know that we're going to use 0.83. 2 decimal places, 0.83. Last one is where we're calculating that residual. The residual, the distance between the actual given point that we have in our sample data and the point that's on our line of best fit, that equation that we have up there. So we're going to use the data point 138 with 131.7. So we're going to use the x value of 138.0, and we're going to plug it into our equation for our line of best fit, our residual line there. And so y hat is going to equal 196.76 minus 0.50 times, I didn't leave myself enough space, so sneak it in there, the 138.0. That should go times that number behind there when you punch it in. So, I'm going to go ahead and put that in there. And so when I do my calculation, hopefully you had time to do your calculation, I came up with 127.76. So the 127.76 would be the y value of the point that's exactly on the line. We now want to find the residual, so we want to find the difference between the data point that we have here and the point that we found on our line. So now we're going to take our 131.7, subtract our 127.76. And if you go ahead and subtract those numbers, hopefully you end up with 3.94 for the value of your residual.